Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome Alistair Miller from Denmark, southern Denmark, from Odense, one of our favorite nodes. And he was here in Warsaw during our quantum symmetries activities, and I convinced him to give a talk. So voila, here he is. And it will be about correspondences, homology, and K-theory for Étale groupoids. It's all yours. Take it away.
All right, thanks. So yeah, as I put in the title, and that's what I'm going to be talking about. So let me just explain a little bit of the sort of motivation and what it is I'm going to be talking about today. So I'm interested in C-star algebras, groupoid C-star algebras in particular, and trying to understand the K-theory of those C-star algebras. So that's illustrated in this sort of diagram here. And okay, there's two questions here, which is why would you care about groupoid C-star algebras, and then why would you care about the K-theory of those C-star algebras? And I think hopefully lots of us have seen K-theory of C-star algebras in a couple of places. And I think it's probably interesting for people who are just care about C-star algebras themselves, through kind of, their help to classify the C-star algebras, for example. And they tell you a lot of information about the C-star algebras. Yeah. And I think they're all K-theory. The C-star algebras is also useful for people who want to use C-star algebras as a tool to do something else, maybe as like somewhere to put an index or something. They ends up being useful in non-commutative geometry in general, I think. And lots of the times when people are interested in a C-star algebra coming from somewhere else, you might be able to actually build that C-star algebra through using an Étale groupoid. So I guess the point here is that lots of the C-star algebras you naturally encounter can be modeled through an Étale groupoid. So you can find some groupoid whose groupoid C-star algebra is the C-star algebra. And you can make this precise for the classifiable C-star algebras in that, everything comes from a twisted groupoid. But yeah, the point I just want to make is that really this is a lot of C-star algebras that we cover this way. And so sort of makes this a natural question to consider. But at the same time, because the C-star algebras are so general, and because the K-theory tells us so much about the C-star algebras, this is going to be a sort of in general impossible task to actually compute the K-theory of these C-star algebras just from the groupoid data. Like, it's too much to ask for, but we can just hope to understand it a bit better. And that's what I'm going to try and do. That's what this talk is sort of aimed at doing, is just trying to understand it better, understand how it connects to some other things, and what can we do with that. So one of the ways people have tried to understand this K-theory that you get a bit better when you look at these special groupoids called ample groupoids, they like to compare the K-theory of the C-star algebra to something called the groupoid homology of this groupoid. So ample means that the unit space is totally disconnected. This is like a zero dimensionality thing. And so it makes it much easier to work with algebraically. And so particular and homologically, so groupoid homology, it becomes much easier in this setting. There's much less geometric content, I'd say. And so people like to try and relate the groupoid homology with the K-theory. And so yeah, this relationship has been developing over the years, and I'll get into that in a bit more detail later on. But the point is I want to think about this diagram and how these things all connect. And what I want to do is I want to upgrade this to something sort of functorial. This picture, I want to make the whole picture sort of functorial. So I want good groupoid morphisms which are going to work with this diagram. So they're going to give us morphisms on the level of C-star algebras, on the level of K-theory, on the level of homology, that sort of thing. And the other thing I'm going to kind of, the direction, what I'm going to use those for is I'm going to use those morphisms to help us understand how the K-theory and the homology link together. So there are already there are already results about how these link together, but then these are going to become a bit stronger with functoriality.
Wait, but do we already know what the bond is between these sequences of abelian groups and pairs of abelian groups? Because it says strengthen, so it would indicate that something already exists.
Yes, so I'd say we have statements about if you just take a groupoid satisfying blah blah and blah, we have statements saying that there is some link between the homology and the K-theory. Sometimes that statement is useful, and sometimes it's not. But sometimes you can get something, but you can create new statements in terms of morphisms, which might be more useful. So
Thanks.
That's the.
I have a question.
Yes, go for it.
So speaking about this bond, do you mean that there's a natural transformation under these admissible morphisms?
Yes, so natural transformation is really.
In which direction? Because on your picture you have two directions. In which direction? It's like Chern character or what is it?
Yeah, more like homology into K-theory. There probably should be some sort of Chern character as well, but I don't know if anyone's actually done that. Yeah.
Thank you.
Yeah, and this is a good time to ask any more questions, so please go for it. All right. And just to show you what sort of things the techniques I'm going to present here are going to be able to give us. There's this computation of the K-theories of certain C-star algebras. And these are C-star algebras, left regular C-star algebras of inverse semigroups. And the idea is that using these techniques, you'll be able to compute the K-theory of this left regular C-star algebra on the left as a sort of orbit stabilizer formula, where these maximal subgroups, these are subgroups of the inverse semigroup. So an inverse semigroup is not really a group, but it does contain these groups in a very canonical way. And it's telling you that the K-theoretic information.
Sorry, Ali, sorry to barge in, but what is E, capital E?
Yes. So you get one of these maximal subgroups for every non-zero idempotent E. So capital E is the set of idempotents in the inverse semigroup. So, and I'll do more on this later. But the point is that each idempotent can serve as the unit in a group.
Yes.
So this is the sort of maximal group that idempotent will be a unit in.
Okay, but what's the difference between E and E cross?
E cross just means that I'm not considering zero.
All right, perfect. Yeah, thank you.
Yeah, so for me, an inverse semigroup always has a zero. And I just want to respect that zero. This is mostly just a matter of convention.
Sure.
Yeah. So the point is that the K-theoretic information of this C-star algebra you build just as a sort of very natural left regular representation. You kind of get a bunch of partial isometries on a very natural Hilbert space. This decomposes into K-theories for group C-star algebras. And sure, it's hard to compute those, but we've changed the problem into, or we've reduced the problem because we've gone from inverse semigroups now just to groups.
So just to sanity check, when you look
Yeah.
at this symbol here, you mean you take the quotient, you divide the cross by S, right?
Yes, so
Because I read it as S minus E cross.
no, this is an orbit space. So
Okay,
so it's like an orbit stabilizer sort of thing. So for each orbit,
Okay,
for each idempotent up to being moved around by the dynamics, then there is one of these guys. Yeah.
it makes sense, but it's also a bit confusing. Okay.
Yeah, no. Please ask any questions like that because I've got time to explain them. And
The minus makes sense.
Exactly. This is why it's confusing, because the minus makes sense.
Does
yeah,
this,
minus makes sense. Yeah.
sorry, does this equation you wrote down just basically come down to the fact that if you have a groupoid which is equivalent to a groupoid which is a disjoint union of groups, then the C-star algebra is just
Yeah.
the infinite direct sum.
Right. So what we've got here is that the universal groupoid, which is the model for this C-star algebra, if it were as you were describing there, it would be something discrete. But this is something that's got a lot of topology. So like the unit space of this groupoid is going to be, I mean, often
But there's a topological version of that also.
So there's a topological version of, so you, as far as I understand, you're saying if the groupoid looks like, if it's equivalent to something which is just the disjoint union of groups.
Disjoint union of, let's say, locally compact groups, then the.
So the topology is in the space direction rather than the group direction here.
No,
So
but I mean, in general, you could have topology in both directions.
yes, but here it's all of the topologies in the space direction. So
Okay, all right. Okay.
Is not going to look like the universal groupoid doesn't look like just something that's equivalent to disjoint union of these groups, because these groups are discrete. But this is actually going to show up in the proof. The point is that these groupoids, so there's a discrete one. You can kind of think of the non-zero elements of an inverse semigroup as a discrete groupoid. And that's the K-theory on the right. So the K-theory of that guy is, because of what you described, what's on the right. And the point is, actually, these techniques, I'm going to be able to compare these two groupoids and deduce that they have the same K-theory.
Okay, great. Okay, thanks. Okay.
Cool. So as just sort of a basic example where this is already known, but just to kind of give you an idea of the flavor of what this is telling you. So there's something called the polycyclic inverse semigroup, which is one of the sort of first non-trivial inverse semigroups that people study. It's very interesting. When you do this, you can quite quickly identify the C-star algebra with the Kunst-Toeplitz algebra. So the extension of ON. And then this tells you that really all you have on the right here, you have one orbit, and you have the K, and you have a trivial maximal subgroup, and you just get the K-theory of the complex numbers. All right. Right, so that was the overview. And yeah, if there's any more questions about this, then do interrupt me now. Okay, great. So now I'm going to sort of tell you about a kind of morphism of groupoids that I'm going to consider called Étale correspondences. And these are going to be the morphisms which are going to make these diagrams work nicely. So we just think about the K-theory picture here. Then we've got a groupoid, we've got our groupoid C-star algebra, and we've got the K-theory groups. And functoriality for the groupoid C-star algebra construction is just a little bit subtle, because you would maybe naively want to consider general continuous homomorphisms of groupoids. So the sort of the obvious structure preserving maps. There's really no way to get anything good on the level of the C-star algebra, or, you know, you can't get a good morphism of C-star algebras out of these guys. And you can see this already by just looking at the extremes of the group case and the space case. So groupoids can be both spaces or discrete groups. Étale groupoids can be discrete groups. And a homomorphism of discrete groups is going to give you a star homomorphism in the same direction with the C-star algebras. Okay, you know, the sum, you know, maybe you have to ask for the kernel to be amenable in order to get something on the level of the reduced C-star algebras. But the problem is even more basic than that, because if you take a continuous map of spaces, you get a star homomorphism in the other direction. So the problem is that the sort of structure preserving map thing gives you morphisms in the opposite directions when you look at spaces or when you look at groups. So it's just going to be completely impossible to get something good at the level of the C-star algebras here. But on the other hand, there's this hugely successful kind of morphism of groupoids that's been used, which you might call a Morito equivalence. And this gives you a Morito equivalence at the level of the C-star algebras. And this works really nicely with K-theory, because it gives you a nice morphism at the level of the K-theory groups. And probably if you pick up a random paper that is about K-theory of groupoid C-star algebras, this will be used, I don't know, at least 5 times. So this is really, I would say this is pretty fundamental. And, you know, as we've already had a comment that alludes to this idea, right? So these are an important notion of morphisms that we want to capture if we're going to make this diagram functorial in a good way. On the other hand, there are these other kind of morphisms which have a bunch of names. So Zakrzewski morphisms, also known as actors or algebraic morphisms. And these are sort of a good notion that will give us star homomorphisms on the C-star level. And therefore, we obviously get homomorphisms of the K-theory groups. So yeah, we want our notion to be something that sort of covers both of these things, because we get this nice notion of equivalence, we get this nice notion that gives us star homomorphisms. And that's what Étale correspondences are going to be. They're going to be something which gives us something which is sort of like, if you combine star homomorphisms and Morito equivalences together, you get something called C-star correspondences. And if these are what's called proper, then you get a homomorphism in the K-theory groups. Proper here should be compared to, like, if you have a proper continuous map of spaces, that's what gives you actual star homomorphisms on the nose at the level of the C-star algebras. Otherwise, you have to map into the multiplier algebra, and then you're not going to get something in K-theory. So that's why we need properness here. But you could also try, and this isn't something I've done, but this is something that you could potentially try, which is you could also try to build sort of Kasparov cycles out of this. So Kasparov cycles are C-star correspondences with a Fredholm operator. And so you could try and do that sort of thing on the groupoid level, perhaps, and then you still hope to get homomorphisms at the K-theory level. But the point I want to make today is that these Étale correspondences really give you a lot of morphisms of groupoids, lots of really natural morphisms, and they show up in a lot of places. So obviously the 2 things I've shown you so far are examples of Étale correspondences. But actually we can sort of fix this continuous homomorphism problem if we just ask for it to be Étale, meaning it's a local homeomorphism. So now, if you have a local homeomorphism homomorphism, then it will give you, you can build an Étale correspondence out of this, and you can run all of this stuff, and you can make this diagram functorial with respect to those. So that includes, for example, open inclusions as well, which, you know, you get a very obvious map at the level of the C-star algebras there. And there's going to be more. And indeed, the example I started off with that made me interested in this doesn't fit into any one of these categories. But it really is sort of an Étale correspondence in itself. But I should remark that every Étale correspondence is some composition of Morita equivalences, Sakoszewski morphisms, and open inclusions. Right. So groupoids. I've already said this word a lot, and now I'm going to draw a picture to justify the word. So the way I think of groupoids is that you've got a unit space, which is topological. I write G0, and the elements of the groupoid are arrows that you draw on this unit space. So like G and H here, and you have rules like for a group. So you can compose arrows when it makes sense. You have identity arrows, and so you can sort of identify the unit space as actual identity elements, like identity arrows within the groupoid. And you have inverses. So if you've never seen these before, these two examples are probably the best ones to think about, and you can just think about that for, you know, most of this talk, which is if you've got a group action, then, you know, you really have this sort of arrows picture in your head already, I hope, where you have arrows labeled by the group elements that move a point to another point in the space. And then these triples where you take the point and the group element and where it sends it, they're going to give you a groupoid. And an equivalence relation gives you a groupoid. And the idea is here, we don't need to think about labels on the arrows. We just have some equivalence relation in our space. Then we draw an arrow if they're related. And we draw an arrow in both directions. And you can easily see that the defining properties of an equivalence relation give you a groupoid. And usually I'll use R to denote an equivalence relation groupoid. Yeah. And I'm talking about Étale groupoids, which means that I only want to consider topology on the space level, and on sort of group direction, then things are going to be discrete. So one way I can think about this is that every arrow G that I've drawn up here on the right is going to have like a fat arrow that it lives inside. And this fat arrow is going to basically biject this neighborhood of X to a neighborhood of Y. And we call this a bisection. But yeah, it's sort of like, it means that we can do our dynamics on the level of these bisections rather than having to sort of think about each, you know, spindly little groupoid element arrow individually. So I need to talk about actions of groupoids, because like groupoids can also act, but we need to take a little bit more care to describe how groupoid actions work compared to group actions. The key difference is that you have this extra piece of data called the anchor map. And this is something which tells you which groupoid elements are allowed to act on which space elements. Because in a groupoid, you know, multiplication is restricted. You can only do it when it makes sense. So this is telling you what makes sense. And the idea is that if you have some space element and some groupoid element, then you want to be allowed to write something like G dot X if X maps down to the source of the arrow G. And then you better make sure that G dot X maps down to the range of G. So everything else is just like a group action, but you have this anchor map. So the sort of most basic example is the trivial action. So this is the analog of a group acting trivially on a point, where now you act on the unit space. And so an arrow is going to send its source to its range. You also have less multiplication. Yeah, really the point is that G.H is GH whenever that makes sense.
Ask you a silly question, it's very naive.
Yes.
Why in the definition of Étale groupoids, you only care about the range map being a local homeomorphism and you don't care about the source map?
Yeah, good question. They're equivalent. So
It's equivalent. Okay.
yeah, so one is a local homomorphism, or both are, or it's all the same.
Okay, just okay.
Yeah. Because you can compose with the inversion.
Yes.
All right. So one consequence of defining groupoid actions is that you find that you've accidentally defined an action of a space. So what does an action of a space mean? It means an anchor map, and that's it. So yeah, so if I say space action, then I mean that the other space is fibered over your space. So an action of Y means that your space X is fibered over Y with this anchor map. All right. So if we have an action, we can build another groupoid, just like we can build groupoids out of group actions. We can build groupoids out of groupoid actions. And it's exactly the same sort of process. And we just denote it the same way with this L times operation. And we call this, so then, yeah, so now I'm going to define some properties of groupoid actions. And unfortunately, the word Étale appears everywhere. It always means that there's some local homomorphism hiding somewhere. But if I say that an action is Étale, it means that this anchor map is Étale, i.e. it's a local homomorphism. So for example, for a group action is going to be Étale if and only if the space is discrete.
And in general, we have a local homeomorphism if preimage of a point is discrete, right?
Yes, exactly. Yeah.
Mm-hmm.
So I guess it's sort of saying that the space is discrete compared to the groupoid.
Yeah.
That's the sort of flavor of having an Étale action. And now you can define freeness of an action in a very obvious way, and properness as well, but together they're equivalent to this statement that if you basically if you take the range and the source together as a map from G cross X to X cross X, you get a homomorphism onto a closed subspace. And this is a condition that tells you that the action is really, really nice. You get a Hausdorff quotient, stuff like that. It's yeah, and it's the sort of thing that you can build Morita equivalences out of. So left multiplication is going to be all of these things. It's a super, super nice kind of action. Yeah. So this allows me to define Étale correspondences now. So it's going to be a
May I have a question?
Go for it.
If you could come back to the previous page about Étaleness of the action.
Yeah.
Is this definition good only to the actions of Étale groupoids?
I suspect so. I don't know. Good question. I mean, I guess to answer that question, I'd first want to understand whether it's like, is it natural for topological groups to act on discrete spaces? So I think that's the sort of question we'd be asking there.
Yeah.
And yeah, I sort of suspect it doesn't feel like it would be a good thing to do, but I'm not sure.
Thank you.
All right, any more about actions?
Well, maybe not about actions, but I Googled finally what Étale means. It means slack.
Yes, it means slack, apparently. And I don't know if that helps, but
No, it makes sense. I mean, I know, but this discreteness, but this is like a covering, you know. It means that the components are not tightly bound. There's some slack. Once you have a discrete space, I mean, you get different components. I mean, you have something, I don't know. You can move them around. They are not tight. And that's exactly the meaning of slack, not being tight.
okay.
In French, that's all.
Yeah. Well, I'm glad it helps you.
Because it's all over the place. I just couldn't resist Googling it up.
Yeah. But yeah, it's become to mean just local homomorphism to me, and or something of that nature. I guess it's, you know, you sort of imagine you could use it in a in a different kind of category than like topological spaces.
Yeah.
All right. So these correspondences are bispaces. What does that mean? We've got some space in the middle, and we've got a left action and a right action. I think I showed you the definition of a left action before, probably, but you can also have a right action. Being a bispace means that these actions commute. So it means whenever you can define these things on some omega in the space, then it doesn't matter in which order you act. And yeah.
No, I was just clearing my throat. Sorry.
Oh, sorry. And yeah, so to be a correspondence, then this right action has to be super nice in the way I was describing before. So it has to be free, proper, and Étale. And this means that it's an Étale correspondence. You can talk about correspondences between non-Étale groupoids, and then you would want to weaken this condition to respect things in a different way, because then Étaleness wouldn't be the right thing to ask there. So that's part of the reason I suspect that it's not a good notion outside of the Étale groupoid setting, this Étale action definition.
And no assumptions about the left action?
No assumptions about the left action. This can be completely general. So you call it proper, and this is you want to think about proper continuous maps of spaces here, because you call it proper if this. So the fact that the actions commute means that you get a map, a well-defined map from the right orbit space to the unit space of the first groupoid. So you have the anchor map, and
sorry, Ali, but what do you mean by dividing a map by a group?
No, omega is a space.
Sorry. Yes. Okay. Yes.
Yeah. So this is an H space, and so this is just the space of.
It's not a map. It's a morphism. Sorry. Of course.
Yeah. So I'm using the yeah, exactly. So it's a morphism in a category, and I'm using the underlying space of the I'm conflating the underlying space of the bispace with the bispace when I write omega from G to H. Yeah. I mean, technically it's all of the data of the actions and everything, but I'm just
So I could comment on Piotr's previous question about this lack of symmetry in the definition of this Étale correspondence. So if you think about Morita equivalence, you can write the Morita equivalence as a bimodule, okay, such that you have no any constraints for the left action, but for the right action, you have the condition that is finite generated projective right module.
Yep.
So this is a parallel to this definition.
Yeah, and I want to say that it's by design that this is not symmetric, because really I want to consider morphisms rather than some kind of equivalence.
Yeah,
Um,
yeah, thank you. Mhm.
So there's a direction in this correspondence.
yeah,
It's like a morphism with a direction.
exactly. And that's important. I really want to think of them that way. So yeah, we have this properness, and the point of this properness,
Yes.
so yeah, this orbit space. So the point is this map row overline row bar, I guess I call it. The right, no, the range anchor map, that's why I've got row. It's row for range and sigma for source. So the range source map, the range anchor map is gonna be invariant under taking orbits in the h direction. So we get a map of the orbit space, and now we just ask for that to be proper. And this is going to give us things which are like proper C-star correspondences, and we're going to get maps in K-theory and that sort of stuff. So that's the point of this. And here's the definition. And indeed, a Morita equivalence is also a bispace with the actions commuting. And here we can ask for both of these actions to be really, really nice, to be free, proper, and Étale. And now we ask for this induced map that we get to be not just proper, but a homomorphism on both sides.
Mhm.
So this is like if you symmetrize everything and make everything as like an isomorphism as possible, you get Morita equivalence. So you can, it's actually true that I'm not going to tell you about the composition of these correspondences, but you can form a category of these guys. Two category. And the isomorphisms are exactly the Morita equivalences. So some examples of Morita equivalences. So here I'm writing Rn for the full equivalence relation on endpoints. So that means every point is related to every other point. I'm sort of writing this groupoid over here on the left in blue. And we're going to get a bispace, which is just the finite set n times n. And you can sort of imagine how these actions work with the left groupoid kind of moves things horizontally, and the right groupoid moves things vertically. And this is sort of, yeah, this is the analog, this is the groupoid analog of the Morita equivalence between the n by m matrices and the n by n matrices.
Yeah, exactly. Mhm.
And you can make n infinity as well. That's also fine. So any groupoid acts on itself by left and right multiplication. This gives you sort of the identity correspondence.
And the anchor map is an identity, right?
So the anchor map is not the identity because it's going from G to G naught. So
It's
the anchor
source or
map
target, source or range, right?
yes, exactly.
Yeah.
And it's whichever one looks like it makes sense for the side the action's on.
Yeah. Mm-hmm.
And then you can get then the unit space is Morita equivalent to if you get the groupoid to act on itself and you take the action groupoid there. And the bispace is just going to be the groupoid.
Nice.
And then this is a nice example. So if you have a continuous, a surjective local homomorphism, then you're going to get an equivalence relation on the first space by do these things agree? Do these things get mapped to the same point in X? Then, so you get an equivalence relation on the left, and then you've got X on the right, and these are going to be Morita equivalent via the bispace Y. So the action of X and Y is the map psi. And the action of the equivalence relation on Y is the action of the equivalence relation on its unit space. It's just the usual action there. Yeah. And then there's a sort of very classical example where you have free proper action of a group or even a groupoid on a space, then you get equivalence between the transformation groupoid and the orbit space. Yeah. So let's move outside of the Morito equivalence world. And so if we have a group homomorphism, this is now a very one-directional thing. You get actions of both groups on the second group, just acting either by right multiplication or through the group homomorphism. And the point is we can mimic this for a groupoid homomorphism as well. But we have to change the middle space a little bit. It's not going to be good enough just to set the middle space to be the second groupoid. So what you do, I mean, it doesn't really matter exactly what you do, but you can create a space, right? And you do it so that it makes sense to write down the same sort of map. So basically the idea is you want to be able to make sense of saying, okay, well, I want to push through the homomorphism and act using the homomorphism on this space. So you sort of modify the second groupoid. You give it access to these elements from the first groupoid, from the unit space of the first groupoid. And in order for this to actually give you an Étale correspondence, you needed your homomorphism to be Étale. So this is how, if you have an Étale homomorphism, i.e. it's a local homomorphism itself, then you actually get an Étale correspondence. So if you started off with an open inclusion, then you get this space, and everything you get the inclusion on the level of the C-star algebras as well. But also there's this this example of the Morito equivalence I gave you on the last slide also gives you an Étale homomorphism. Just using psi gives you a homomorphism from the equivalence relation to the space X. And you're going to get exactly the same correspondence out of this procedure as the one I showed you on the previous slide. So this third kind that we cover, these are Zakrzewski morphisms. And I think these were first really studied at least in the operator algebraic context by Bonecci and Stachura. And it's an action of the first groupoid on the second groupoid that's compatible with right multiplication.
It's quite possible that I don't remember, but I think Stachura was a student of Zakrzewski.
Oh, okay. Sure. Yeah, and these things, it's not a completely obvious morphism of groupoids, but it's an extremely useful notion of morphism of groupoids. So I think they basically get rediscovered in lots of places. Yeah. And so they have at least 3 names. But yeah, this is one of them. And yeah, so for when you just look at groups, this exactly means a group homomorphism. When you look at spaces, it exactly means a backwards continuous map. So we've solved our directionality issue that we had. So really, I think this is the right generalization of group homomorphisms or continuous maps to the groupoid level. And you get something at the level of the C-star algebras as well. And in general, it's going to be, you get a star homomorphism into the multiply algebra. But if it's a proper correspondence, because what I've described to you here is just by definition, you can see that it is a correspondence. This is a nice, this space has all we need was the conditions on the right multiplication, and we have those conditions. It's the nicest possible action. But yeah, so if that's proper, then you get an actual star homomorphism. So for example, you can have an open subgroupoid. Here we need it to contain all of the unit space.
So I'm confusing your third dot. When you have this G curved arrow H, you mean that there is a Zakrzewski morphism from G to H, right?
Yes, so
Not an action of G on H.
right. I mean, not just so. Yeah, I will. Sometimes I will write G acting on H to mean this is actually a Zakrzewski morphism, i.e.,
Okay,
commutes with the right multiplication. Yeah, but it's. I agree. There's something to be said there. So if you just had G acting on H as a space and it said nothing about the groupoid structure of H, then you wouldn't be able to say anything at the level of the C-star algebras, obviously. Yeah. So one class of examples of these is if you have an action, then it gives you a Zakrzewski morphism from G to the action groupoid. And really, you just do the obvious thing here. It's not deep. But this is going to be proper if and only if the anchor map is proper. And a slightly more interesting example is this is something that some C-star algebraists have considered. So these guys actually appeared when Xin Li was building his groupoid models, twisted groupoid models for classifiable C-star algebras in the stably finite setting. And what you have is a backwards homomorphism of groupoids, which is surjective and it's proper, and it's got this fiberwise bijectivity condition, which is a little bit of a mouthful to write out, but really you can realize that what this is doing is it's allowing you to define an action of G on H. So you can build this action of G on H from this data using the fiberwise bijectivity, and you're going to end up with a proper Zakrzewski morphism. So I think this is quite a nice example, actually. And sort of further evidence of these morphisms is a good class to consider, especially when you're considering about star homomorphism, especially when you're considering star homomorphisms with C-star algebras. Right. And yeah, the point is just to bombard you with examples of lots of different places that these correspondences can come from, because I want to try and convince you that they're a good thing to study. And so if you just have spaces, so you think of spaces as groupoids with trivial arrows, what does an Étale correspondence mean now? It just means you've got two maps and one of them is Étale. So your space and two maps to your two spaces. So a nice example of this is if you've just got an open cover of your space, any space Y, then the disjoint union of these opens will be your bispace between the index set and the space Y. Here we're including the disjoint union, or not including, we're including each open from the disjoint union into Y. That's this right map. And then the left map is just picking out the index.
So I'm a bit confused. So you want UI to be both open and compact?
If I want it to be a proper correspondence, yes. But
there will be
working
like...
with totally disconnected spaces, this
Okay.
happens.
Okay.
So it's a sensible thing to consider for totally disconnected
Yeah,
space.
connected components can be open.
Yeah.
Compact.
Yeah. It's
Mhm.
exactly. But if you don't want it to be proper, then you don't have to ask that.
Yeah.
Maybe, I don't know, maybe you just want to construct some sort of Kasparov cycle. Then you don't need to care about, you won't need to have to find any compactness. You'll just look at opens, and then presumably your Fredholm operator you try to build on top of all of this will sort out your problems. But yeah, I don't know. So now I'm going to talk about the sort of, for me, what the motivating example is. So if I start off with an inverse semigroup, And I want to think about an inverse semigroup as an algebraic object of partial symmetries. So a partial homeomorphism, for example, in the same way that a group is an algebraic object of symmetries, right? So a partial homeomorphism is a homomorphism between two open subsets of your space. We can also look at open bisections in an entire groupoid, which are these fat arrows I drew earlier. I want to consider this as like a partial symmetry sort of within the groupoid, right? And partial symmetries, the way that you compose them usually, it's sort of this picture, right? So if you have a partial symmetry T and a partial symmetry S, their composition is going to be sort of wherever it makes sense to compose them. So T is going from this entire ellipse on the left to this ellipse in the middle here, and S is going from this ellipse to this entire ellipse on the right, but their composition is only going to make sense from the shaded red regions. So a good example of an inverse semigroup is this polycyclic inverse semigroup on N generators, which you can view as the star semigroup that you generate with the Kunz isometries in the Kunz algebra, ON. I'm pretty sure. So, and this is something, you know, it similarly has a universal property in the algebraic context. And it's something that people who like inverse semigroups study. So I'm always going to use E to refer to the semilattice of idempotence. So an idempotent is just something that squares to itself. But what that sort of means in the partial symmetry point of view is that it's the identity on its domain. So you could think about, you know, a partial homeomorphism is an idempotent if it's the identity on some open subset. Or an open bisection is an idempotent if it's just an open subset of, like, it's an open subset of the unit space. So it's just units. So now we're going to associate two groupoids that we want to study. One of them's discrete, one of them's ample, so it has totally disconnected unit space. So the first one I'm going to call the underlying groupoid, because it really is just the elements of the inverse semigroup, but I'm throwing out 0. And the composition is, well, first of all, the unit space is the non-zero idempotence, right? Because you think of each element in an inverse semigroup as having a source and a range. Like a partial symmetry has a source and a range. Partial homomorphism has its sort of open set that is its source, and it's got the open set that it's domain. And so these are going to form the units for this discrete groupoid. And then the composition is just composition. And now this really is composition of functions, because you've set it up so that the domains and the ranges, they actually match up. The universal groupoid, I'm not going to go into the full technical definition of it, but I'll tell you about its unit space. So the unit space of this one is the filter or character space of the idempotent semilattice. So the semilattice is closed under multiplication. You think about this as like intersection of domains. So you can ask for a character on that. And I'm just asking for non-zero characters. We might call these filters because it's also equivalently an order theoretic thing. And then this has a nice totally disconnected topology. And we have these compact opens for every non-zero idempotent. We have all of the characters, filters that evaluate to 1 on that idempotent. So the point is that even at the topological level, we get a sort of interesting correspondence, because I've just given you an open cover. So from this open cover of our nice, interesting topological space, we get this correspondence from the discrete one to the interesting one, given by this disjoint union of all of these opens. And then this can actually be upgraded into a correspondence from our underlying groupoid to the universal groupoid. And so now what appears in the disjoint union is not the open set UE, but all of the groupoid elements in the universal groupoid whose range lands in that UE. And so that's what makes this action work. And because these open sets are compact, we get a proper correspondence on the topological side and also on the groupoid side. So on the right, we get this nice proper Étale correspondence. So this is my motivating example, really, of a correspondence that got me interested in these things.
Could you explain the meaning of the middle symbol on the right-hand side at the bottom line? Lower. This joint union over this non-zero idempotence.
Yes.
And then?
Yeah, not obvious what you need.
Functions, fixed points.
Right. Yeah. Sorry. No, this is something I haven't explained. So thanks for pointing that out. Often when we work with groupoids, we will write something. If we write a subset of the unit space to at the top of the groupoid, this means we're restricting to all of the groupoid elements whose range lands in
okay.
in this case.
Mm-hmm.
Yeah.
So the upper index is for the range.
Yes, upper index is for range. Lower
And the lack of the lower index means
source.
this is for whatever. So these are arrows ending at UE.
Mm-hmm.
Yes, this is arrows ending at UE, and lower in this. I don't care where they start.
Okay.
Yeah.
Okay.
Yeah. Yeah. Cool. So let's just go through a summary of all of these examples I've given you of Étale correspondences. So we've got Morito equivalences, which we want to have under our belt because they're used all the time. We've got Étale homomorphisms. So yeah, so for example, we can do any open inclusion. We got our Zakajewski morphisms, which can come from actions. They can come from these surjective proper homomorphisms.
Sorry, are you sure you want that N here? I mean, you are a native speaker, but why?
I definitely don't want that. No, I think what's happened is
Copy and paste.
yeah, no, I think what's happened is I probably called it an actor or an algebraic morphism or something.
And outside morphism. Okay. Mm-hmm.
Yeah,
okay.
so this is definitely a Zakajewski morphism.
Yeah. Okay.
Thanks. So for spaces, we get sort of open covers, give you these things. And then this example I'm interested in. So if you start off with an inverse semigroup, you get this thing that I constructed in the previous slide. Yeah. So now let's talk a bit about homology and K-theory. Although we can, if you want to ask any questions about these examples, then now's a good time.
Well,
Cool. So let's just look at this this diagram again that I showed you on the first slide. And
so can you remind me what ample point is? I know, but it must be Étale, right? But
yes, so ample means that the unit space is totally disconnected.
okay, thanks.
Yeah, exactly that. So it means everything's easy in that way. And so, for example, all of these, like this inverse, the universal groupoid that I talked about here for the inverse semigroup GS, that's ample because the space I told you was the space I told you about was totally disconnected. So yeah, let's look back at this picture. We're thinking about homology and K-theory, and and we know that, yeah, so the point is that we can now try to make this diagram functorial with respect to correspondences. But I also first have to tell you a bit about, okay, what are these question marks and everything. So let's see what happens. So first thing is that these people have constructed C-star correspondences from Étale correspondences. And what's happening here is Holkar was doing this in the sort of non-Étale setting, but then I guess not quite as generally in other directions. And then the 3-author paper here kind of ironed out the details for, you know, general non-Hausdorff Étale groupoids. Yeah. And so what this means is, if this thing is proper, we get a map in K-theory, because we know already that proper C-star correspondences give you maps in K-theory. So that's good. That's sort of the top layer of our diagram sorted now. We're very happy about that. But let me tell you a bit about groupoid homology. So now we're assuming ampleness, which means that we can study it very easily algebraically. So I'm going to call this thing the groupoid ring. This is the function, the continuous functions from G into Z. If G is not Hausdorff, I'm slightly lying, but only slightly. And it's got convolution, which turns it into a ring. And, you know, I'm slightly lying. It's not a ring. It's locally unital, not necessarily unital. But, you know, if we work with non-unital C-star algebras, we should be comfortable with locally unital rings. Now, if we've got a ring, we can talk about modules. So I mean a non-degenerate module, because of the local unitality, I have to say something instead of that the unit acts as a unit. I have to say non-degenerate. And so an example, sort of a great source of examples of G modules is from G spaces. So if your space is totally disconnected, then you can consider this space of continuous functions from X into Z and sort of do an action in the obvious way, and you get a nice G module. So you get nice abelian categories of left and right G modules, and there's a tensor product, which spits out an abelian group, because things are non-commutative. And now we can define groupoid homology, which is, if you know what Tor means, the Tor functor, then it's just that, as I've written here. But there's another way to write this down, which is there's an explicit chain complex that I sort of hinted at here at the bottom here. You can write down that Matsui wrote down, and the homology of this chain complex will be, oh, I've done that thing again. I think, now maybe I'm okay with that being the same n as this n. I don't know, but in theory that doesn't have to be the same n as this. I just wanted to show.
No, it's different.
As a dummy index.
Yeah, one is a dummy index and one is not. Yeah, so it shouldn't be n. But can you explain what this g to the power n means? Because I'm somehow.
Yeah. So yeah, that's something I haven't done. So g to the n means the space of composable n tuples of arrows. So g squared is the pairs of composable arrows that you define multiplication with.
Kind of like path of length n.
Yeah, path of length n.
Okay.
Yeah, exactly. And this is always what you want to consider with groupoids. You always want to, when you want to take products of spaces, you always want to restrict to where things actually make sense.
Is it the same as the geometric realization of classifying space of a groupoid views as a small category?
Yeah, it's that sort of thing.
Okay.
Yeah. At least this chain complex is coming from that sort of place. Yeah, so it's sort of like it's coming from a bar complex like thing.
Yeah, so maybe it's not about realization, it's more about the simplicial model for BG.
Yes, that's right. That's more accurate.
Okay, thank you.
Yeah, sure. Any more questions about this, by the way?
I don't have any more questions. Thank you.
Cool. And yeah, just a quick note that, you know, Tor does still make sense, even though these are locally unital rings and everything works just fine. Yeah. So one of my results says that these correspondences, the proper ones, they do give you maps in homology. So this is factorial. And as an example, this one I'm interested in, it's actually quite easy to write down. You just do a sort of computation and you see that this thing is an isomorphism. So I find this quite interesting because the groupoid on the left is very discrete. The groupoid on the right is very topological. But they turn out to be homologically exactly the same and even witnessed by something, by some morphism. Yeah, and I want to make a quick comment about what this means for Morito equivalences. So because this thing is functorial, this recovers the fact that Morito equivalences induce isomorphisms in homology. And actually, you can get quite a nice if you get quite a nice idea of how this proof goes by just thinking about the Morito equivalence case, because what's happening is that this bispace omega is giving you a bimodule, because G spaces gives you G modules and H spaces give you H modules. The bimodule gives you an equivalence of categories between the module categories by construction, basically. And so what's happening here really is that this isomorphism in homology that you get from a Morito equivalence is coming from an equivalence of the module categories, which you hope from the name Morito equivalence is true. But yes, it is. So yeah, I thought that's quite nice. So you get this example that's an isomorphism, and this allows you to compute the homology of this universal groupoid in terms of these maximal subgroups from before. Because this discrete groupoid here is just Morito equivalent to the disjoint union of all of these guys over this sum.
Yeah, so now you are writing orb of E instead of
which is
class of E.
Yeah, which is much better notation, I agree. And there's a reason I did it here and then I obviously forgot to change it in the other one. Right, yeah. And so now this is really just group homology, which is more classical than groupoid homology is, right? And there are many, many tools that are there in order to try to compute this thing. So the relationship to K-theory, well, there's this very naive guess, which is that the K-theory of the C-star algebra could look like just the direct sum over the indices of the same parity of the groupoid homology. And basically, this is coming from a bunch of examples in the sort of, so this is coming from a bunch of examples for topologically free groupoids coming from topological dynamics. And so it's obviously wrong just for groups. And so I guess the hope was that some kind of principality, like topologically free, could help us avoid the problems that are there already for groups, because groups are the opposite of being principal, basically. But it turns out there are counterexamples that are topologically free. And really what's going on here is these examples that Eduardo Escaparo built from odometers. They have torsion in the isotropy groups of the groupoid. And this messes things up because in the group setting it's the torsion in the group that really makes this an egregious statement to make. But it gets worse. And really, you know, in high dimensions, you really can't expect this at all. And so Robin Dealey has this principal counterexample that he made. And basically the point here is that the relationship is going to be more complicated. And this technique can be pushed down to 4 dimensions by, and this was done by his PhD student, Rachel Chaser. But then we do have some actual positive results that's sort of true in general. And here, Valerio and Makoto, they showed that it's true if your groupoid has torsion-free isotropy, it's amenable, and the homology vanishes for 3 and above, and it's free abelian for 2. So what's really happening here, and I think this is the sort of more the truer nature of the relationship, is what they showed is that you have a spectral sequence. So the main things we need here are obviously ample groupoid, torsion-free isotropy groups, and it has to satisfy something called the Baum-Kohn conjecture, which is true for any amenable groupoid, thanks to a result of 2. And it can actually, it can satisfy the Horrocks property as well, more generally. But then you get a spectral sequence, and on the second page, you have the groupoid homology, and it converges to the K-theory of the C-star algebra. And just a couple of quick remarks is that originally they wrote this for something slightly stronger than assuming the Baum-Kohn conjecture for the groupoid. But thanks to a later paper by Valerio and Christian Bernecker, it actually is enough to just assume the Baum-Kohn conjecture on the nose for the groupoid. And the other comment is just that if you know what the Baum-Kohn conjecture says, then you might be able to guess what this spectral sequence converges to in general. Because actually what's happening is that this always converges to the left-hand side of the Baum-Kohn assembly map.
Okay.
Could you come back to the previous page?
You mean in the spectral sequence?
No. The previous slide.
Sorry, what's that?
You were frozen for a while. Can you come back to the previous slide?
Oh, yeah.
About this project Yamashita. So this looks like it was in the spirit of Hurewicz map between homotopy and homology somehow. If you think about K-theories as homotopy.
Yes, right. So this is very analogous to the classical situation of
So my question is
spectral sequence.
Okay. In the light of this remark, I would like to ask a question about the next slide, about this theorem. What is the source of this spectral sequence?
Source? In what sense? So this spectral sequence is the ABC spectral sequence.
Because
the Meyer-Nest framework.
Nest framework.
So Ralph Meyer and Richard Nest built this framework for homological algebra in triangulated categories. Here we're using KKG as a triangulated category, and so there's this spectral sequence that's built by Ralph Meyer.
How is it related to KK?
How do I relate this to KK?
Yes.
Yeah, I mean, this is what they do is you so you have groupoid equivariant KK theory,
Yes.
which you can study the K theory of the groupoid C-star algebra using.
Mm.
So this thing is going to be a nice triangle, a nice homological functor on that guy.
Yes. Yes.
And then the spectral sequence has these things called, well, it has a form of derived functors on the second page.
Mhm.
And really the content of what these guys did was they identified those derived functors as groupoid homology.
Aha. So groupoid homology appears as a homology of some resolution used to compute this derived functor.
Yes, exactly.
Okay. In one column. Yes.
Yeah. I just
Thank you.
all right.
Mhm. Mhm.
Right. How am I doing time-wise?
You have 15 minutes.
Okay, great. I think that should be fine. Yeah, and also I should remark, you know, they can add coefficients, so the groupoid can act on a C-star algebra, and it's all about, you know, bound conjecture with coefficients and that thing, etc., etc. But yeah. Okay. So now we've got sort of a picture of these things. We know what in my opinion is sort of the you know, what's actually going on between homology and K theory here. This is sort of this spectral sequence is sort of the thing that we want to turn into a natural transformation in some sense, right? And we have, you know, the top here is nice and functorial with respect to our correspondences. We know the bottom here is functorial with respect to our correspondences. So my main result says that this spectral sequence is functorial. So meaning if you have a proper correspondence of groupoids, you get an actual morphism of the spectral sequences, and everything matches up, and everything's compatible. So why is this good? Why is this useful? Well, it means that we can turn an isomorphism that happens at the second page of the spectral sequence into an isomorphism of the target groups.
Mhm. Mhm. Yes.
Because I want to think about a spectral sequence as, I mean, even if you've got no idea what a spectral sequence is, the way I want to think about it is that the thing on the right is built out of the things on the left in a really complicated way. So in the same sort of manner as if you have a short exact sequence of abelian groups, the middle group is built out of the outer groups, right? But maybe you can't always recover the middle group from the outer groups, but you at least know that it's built out of them in some way. And I claim that a spectral sequence is like that, but just 1,000 times more complicated.
Just a stupid question, if I may. So when I want to look at spectral sequence as a function, yeah, then I understand the domain, the category on which it is defined. But what is its target category? Abelian groups. What is it? What is the target category for the functor of constructing a spectral sequence?
So I'm claiming that this construction of the spectral sequence from groupoid G is functorial. So the target category is the category of spectral sequences.
Okay.
So all pages, all differential.
Okay. Mm-hmm.
And in fact, it's the target category is really the category of convergent spectral sequences with like target group and everything, right?
Okay. That's okay. Mm-hmm.
So the point is, if a spectral sequence is like a big short exact sequence, and you have the point is if you have an isomorphism of short exact sequences, no, if you have a morphism of short exact sequences,
Yes.
and you know it's an isomorphism on the right and on the left,
Yes.
it has to be an isomorphism in the middle.
Yeah, 5 lemma.
Exactly, 5 lemma. So this is why morphisms can tell you a bit more about how the middle is made up out of the things on the
Yeah.
side. And it's exactly the same with morphisms and spectral sequences here. If you have a morphism of spectral sequences, which is an isomorphism on the sort of building blocks on the second page, that has to build up to an isomorphism of the target groups.
I'm very happy I asked my stupid question because I think it clarifies a lot what you just said.
Cool. And so that's exactly what this corollary says. It says that if we have an isomorphism in homology, assuming our groupoids give us these spectral sequences, then we get an isomorphism in K-theory. If that isomorphism in homology is coming from a proper Étale correspondence. So this is how we get this K-theory result for the inverse semigroup C-star algebras. And the proof is, well, the C-star algebra on the left is the C-star algebra of the the universal groupoid, GS. And the thing on the right is just the K-theory of the underlying groupoid. So we know that this correspondence gives us an isomorphism in homology. So by the result, we know that now it must give us an isomorphism in K-theory, and that's exactly this isomorphism here.
And again, you need the Baum conjecture only to put here K-theory, not K-homology, the left-hand side of Baum.
Yes, precisely.
Okay.
Yeah. And so this this was known previously under some stronger assumptions on the inverse semigroup. And so the sort of assumptions that were made before was that you have some nice map into a group called an idempotent pure partial homomorphism. And the point of this map is that it means that the dynamics of S can be sort of governed by a group in some way. Like you can describe all of the dynamics you'd want from S as partial actions of the group in some way. And what that allows you to do is it allows you to work in, you can just work in KK gamma for everything. You can do everything with respect to this group. And you can apply something called the going down principle. And so in some sense, these techniques are like a sort of analogous to a sort of going down principle for inverse semigroups-ish. There's sort of, morally, there's some connection there, but I don't think it can really be made precise. But that's the point. And but this is quite a strong condition to make on an inverse semigroup, at least from an inverse semigroup theorist's point of view.
Sorry, I have a stupid question. I don't understand the last remark.
Yeah.
About this extension, because your corollary is about countable inverse semigroup, but in result of Lie, you homomorph from S cross to G to gamma to some group.
Yeah.
So so what is the relation between where is gamma description?
My point is that in the previous results, there has to be this assumption that there exists some idempotent pure partial homomorphism.
It was used, but the result was the same.
Yes.
Okay.
Or I think technically what they assume is that so the Baum-Kohn conjecture for them appears in the group rather than in the universal groupoid.
So this homomorphism to gamma was technicality, the assumption which helped them to prove an analogical result with yours.
Yeah.
Okay, good.
Well, again, if the group satisfies the Baum-Kohn conjecture in this scenario, then the universal groupoid also will. So just yeah.
Thank you.
I should mention, these are both in some sense partial extensions because here I'm assuming torsion freeness. Wasn't assumed by Lie. And here I think they consider locally compact groups and stuff. But in each direction, there's always a bit of extension in one direction, and maybe you add a couple more assumptions in a different direction. But Yeah, the torsion freeness is just so that we get the actual relation to groupoid homology. In theory, this should be true without torsion free.
Mhm. I have a question.
Yeah.
Would you expect some generalization of this corollary for groupoids more general than those coming from inverse semigroups?
Yes. So in fact, I don't know how much more general this is, but like morally, but so okay, so the key thing is that these C-star algebras are sort of like tuplets type C-star algebras. So they're like so I have a class of examples actually, which I'll show you on the next slide. So maybe that's yeah. So if I just give you this thing here,
Thank you very much.
these are the ones I've given you on this slide are all it's been set up exactly so that you get the inverse semigroup C-star algebras. So it's the same thing. But the point is that actually you can weaken this singly aligned condition. So I'll talk about that at the end of this slide, and so I'll come back to your question.
So sorry, to be sure, in the case of the left cancellative small category, do you have an analogous construction of GS? Are you going through some groupoid?
There is an analogous GS, yeah.
Okay, okay, thank you.
Which, if you assume singly aligned, is going to be just the same thing. Because from this you can always build an inverse semigroup here from this thing. But in general, if you don't assume singly aligned, then the groupoid changes a little bit. And those groupoids, under some other conditions, you can get these K-theory formulae for. So the point here is you start off with one of these things, and I think if you've not seen these left cancellative small categories before, what I want you to think about is the category of finite paths on a directed graph. So you have composition is concatenation. Or if you have a category with one object, this is a monoid. And the point of left cancellative is that when you get the category to act on itself, it's going to act by injections. So then it will generate an inverse semigroup of partial bijections, because now you take injections, you take their adjoints or their inverses, and you compose things, and you end up just looking at partial bijections. So if you take the free monoid on n generators, you get the polycyclic inverse semigroup. And this singly aligned condition is going to mean that the C-star algebras you get are just the same thing. So here, the C-star algebra is the left regular C-star algebra. So acting by injections on itself will ensure that you get a bunch of partial isometries on the L2 space of lambda. And you get a C-star algebra that way, which is called the left regular C-star algebra. Then this underlying groupoid is going to be Morito equivalent to the groupoid of invertible elements in your category. And then you get this K-theory formula, which tells you that actually the K-theory of the left regular C-star algebra is just the K-theory of this discrete groupoid of invertible elements. So then to come back to, what about examples of formulae of this kind outside of the inverse semigroup case? Well, this formula here at the bottom has sort of nothing to do with being singly aligned in some sense. Turns out you can weaken it to asking for something called finite alignment, but not general finite alignment. I have to assume a sort of manageability condition on the finite alignment itself. The point being, singly aligned is sort of like saying if you multiply two things together, or if you sort of intersect two things together, then you're going to be able to write it as one other thing. Finitely aligned says you can write it as the union of finitely many other things. What I need is that now you're looking at those finitely many other things, now you intersect those, you get another finitely many things. And the point is this process should stop at some point. And that's the sort of thing that I can generalize this to. But yeah, this is my last example. So that's it. Thanks.
Thank you so much. Perfect timing. According to my atomic clock, you extended your talk by 20 seconds, which is remarkable. Any further questions? Anybody from the room? No?
Yes, I have a question. I have a question about this corollary. There's an assumption, still the standing assumption that it is cancellative small category.
Yeah, so left cancellative is fundamental.
Okay, so you are using this for left regular representation being faithful, probably.
Not just faithful, but actually like acting by bounded operators.
But bound.
Making sense of
boundedness. Okay.
Yeah, so if you don't act by injections, then the sort of formula you want to write down, because you want to write down the operator that corresponds to this injection, or not injection, but this map. But it doesn't necessarily make sense if you don't.
Yeah, it's not, there are not groups. Yeah. Okay. Okay. So what about this hierarchy of different completions of C star with some decorations depending on different completions? Because if you have this regular representation,
yeah,
sometimes it's not most convenient for the bound conjecture, and people consider this ladder of different completions.
Exactly. We have exactly.
For instance, there's a condition of exactness.
Yeah, yeah.
What relationship between this exactness and assumptions about this lambda would you expect?
Right. So for the bound-con conjecture, people consider different, maybe different completions which have, for example, that are exact. And here we've got left cancer to small category. I don't know if there's a natural way to talk about just from left cancer to small category, whether you can talk about some sort of minimal exact C star functor in some sense. I'm not sure if that I guess you can probably make sense of that because you can talk about yeah, you'd probably have to look into fell bundles over what are they're not called fell bundles over the left cancer to small category, but that's what they are. They're called product systems, I think.
Which systems? Product systems.
So this is the sense in which a left cancer to small category can have coefficients in a C-star algebra. So you'd have to consider that functor that sends those to their cross products and talk about exactness of that. And so maybe you could start talking about a minimal exact thing, and then you'd hope that that would correspond to the minimal exact cross product with respect to the groupoid you build. And then you can do bound-con machinery in the same way. And if it works, then it works. And, you get these things. It's just a question of making sure that things would actually match up on the groupoid and the left cancer to small category level, so that you can make your statements right. Yeah. I think.
Thank you.
Sure. I just have a stupid question. What is the difference between lambda and R in your last slide?
Yeah. If I'm honest, if I was confident enough, I would always write lambda because it's a left regular representation.
Right.
The community has decided upon reduced.
Okay.
Okay. But whenever I ballsy enough, I write lambda. I should just write it all the time. But yeah.
Okay. Okay. I'm happy. All right. Any questions from the Zoom? Jonathan, Mark, Richard, Fire and Will, Ludwig. I'm scrolling, but I see no volunteers. Okay, the Zoom is not raising any questions. So in this case, I have no choice but to thank the speaker again. Thank you so much. Let me stop our recording.